Okay, we have a series. This one has a product in there, k times e to the negative k. So we're going to do the integral test because this is monotonic decreasing and because we don't have negative terms in there. No matter what we plug in, we're going from 1 to infinity. This just means that e to an exponent is in the denominator. Doesn't mean the terms are going to be negative. They're always going to be positive. And they're always going to be decreasing because we have an exponent that's getting larger and larger and larger in the denominator. So each successive term is obviously going to get smaller with each round as your denominator grows larger. So we can definitely use the integral test. We use the integral test on this, and so we get ke to the negative k dk. So what are we going to do with this one? We're probably going to have to do integration by parts because it's a product and it's been a long time, but with integration by parts, it's uv minus the integral of v du. So what are we going to take the derivative of? Well, we usually want to take the derivative of something that becomes simpler. So which one would go away if we take its derivative? That would be k. So let u equal k, and the derivative goes away, so that makes this 1, in other words, so it's just dk. And so then u, and then v, dv is the rest of this, is e to the negative k dk. That's k, negative k. So v would equal negative e to the negative k. So we have uv minus v du. That would be negative k e to the negative k, uv minus the integral of v du, which is negative e to negative k dk. The integral of this would give us negative k e to negative k. This would be positive e to the negative k. If you work through all your ways around, you would have a positive in there once you evaluate the integral, but since you're subtracting, yeah, that would be negative. That would be negative. You'd get a positive from your evaluation of the integral, and then you would get just this negative because you're subtracting. So it would definitely be a subtraction here. Now we can do our two different pieces, right? Because with all of this, we had our bounds from 1 to infinity. From 1 to infinity over here, really. And we had to take the limit as t approached infinity because we can't work with an integral that has infinity in there. So now that we've evaluated this by doing it into parts, we look back at what our bounds were, and they were from 1 to t, and we're taking the limit as t approaches infinity. So we have our two pieces here, like this, and we take the upper bound into here. This would be negative t e to the negative t minus e to the negative t, and our lower bound over there, which would be negative e to the negative 1 minus e to the negative 1. Take the limit as t approaches infinity. So with this one, notice that we have a negative exponent, which means that this is the same as having negative t over e to the t. So we're plugging infinity into here, and we're plugging infinity into here. This infinity is going to grow much faster than the other one because this one's an exponent. This one's an exponent, so that's going to go to 0. When you have an exponent that's negative like that, that's going to 0. So this would be 0 minus, again, 0, because we have a negative exponent. Even more so, it's even more obvious in that case because we have just e, right? And the other one we actually had a variable into which we were plugging infinity. This one's just e, and so that's, negative 1 over e to the t. So this is obviously going to 0. You have an infinite denominator. So our answer, our real answer, is you distribute this negative, which would make all of this positive. So 1 over e plus 1 over e. Therefore, since the integral converges, the series also converges.